In this video, I will show you how to integrate some trigonometric functions by transformation of trigonometric formulas. So in my previous video, I've discussed the formulas to be used, and I also give some examples given the sine and cosine functions. So now, I will show you some examples of integrating the other trig functions, the tangent, cotangent, secant, and cosecants. So, in transformation of trigonometric formulas, if we're going to integrate a function, for example, tangent raised to the power of n of x dx, or a function of cotangent raised to the power of n of x dx, where our n here is an integer, so the formulas what we're going to use is the tangent squared of x is equal to secant squared of x minus 1, and in the cotangent function is cotangent squared of x is equal to cosecant squared of x minus 1. So for example, if we're going to integrate a function, for example, tangent squared of x dx, where our n here is 2, which is an integer, so what we're going to use is this formula for us to make it easy to integrate. So by substituting the formula or by transforming, it would be equal to the integral of secant squared of x dx minus the integral of dx. So therefore, by integrating, so in this first term, so now as you can see, we can easily now integrate this function. So the integral of secant squared of x dx is simply equal to tangent of x. Then the integral of dx is simply an x. Then add an arbitrary constant. So that was our final answer. So now, how about we're going to integrate cotangent of squared of x dx. So as we all know, by transformation of the formula, what we can use here, because the power is an integer, so we're gonna use these formulas. So our cotangent squared of x is simply equal to cosecant squared of x minus 1 dx. So by integrating, we're gonna distribute the integral sign each terms. So we have to integrate cosecant squared of x minus the integral of dx. We have dx here. So in simplifying, in our formula, we have a value of the integral of cosecant squared of x, which is equal to negative cotangent of x. Then the integral of dx is simply an x. Then add an arbitrary constant. So that is our final answer. So how about if we're going to integrate a function, for example, tangent raised to the power of 3 of x dx. So as you can see here, our n is equal to 3, which is an integer. So also, what we're going to use the formulas of tangent squared of x is equal to secant squared of x minus 1. So therefore, in order to use this formula, we need to break down this function. So it would be equal to tangent squared of x times tangent of x dx. So we can now substitute this function to this function. So it would be equal to the integral of secant squared of x minus 1 times tangent of x dx. So by distributing, we have the integral of secant squared of x times tangent of x dx minus the integral of tangent of x dx. So in simplifying, first in this term, as you can see that the derivatives of tangent is equal to secant squared x, therefore we're gonna represent this as u. We use in this term the du and u representation and substitution. So we're gonna represent the u as equal to the tangent of x, because the derivatives or the du is equal to secant squared of x dx. So therefore our dx here is equal to du over secant squared x. And if we substitute this our representation to the original function, we can cancel out the secant squared x. And by substituting, we have the integral of secant squared of x. Our tangent x, we represent this as our u. And our dx here has a value of du over secant squared of x. So it's be cancelled out. So therefore, in this term, it's become the integral of u du. So now in this term here, to integrate tangent x dx, what we're gonna do here is to substitute tangent x by its equivalent to make it sine and cosine function. So as we know, tangent x is equal to sine of x over cosine of x. So therefore, gonna be equal to sine of x over cosine of x dx. So as you can see here, to integrate this function, so you can see the derivatives of the denominator, which is negative sine of x, is equal to the numerator. So we can represent this denominator as our u, and we use du and u representation and substitution. So therefore, we're gonna represent our u is equal to cosine of x. Then our du will be equal to negative sine of x dx. So therefore, our dx here is equal to du over negative sine of x. So by substituting, we have the integral of sine of x over u. Our dx has a value of this du over sine of x. So now as you can see, we can cancel out this function. So what's remaining here? So the answer for this is the integral of u du using the power formula of integration. So we have u squared over 2. We had the exponent by 1 and divided by the function by its exponent. So now in the next term, what is remaining here is the integral of minus, because we have minus here, du over u. So by simplifying, we have our u here is equal to tangent x. So we have here tangent squared of x over 2, then minus, then the integral of du over u using the, so we can use here the logarithm formula of integration. So we have ln absolute value of u plus absolute value of u plus an arbitrary constant. So in simplifying, we'll be going to equal to 1/2 tangent squared of x, then minus, so our u here is equal to cosine, so we have negative ln absolute value of cosine of x plus c. So in this function, we can simplify this as figure here. So in this function, we can simplify this, so it would be equal to 1/2 of tangent squared of x. In this function, it's gonna be equal to ln cosine raised to negative 1, cosine of x raised to negative 1 plus c, where cosine raised to negative 1 of x is simply equal to 1 over cosine of x, then it's equal to secant of x. So therefore, by simplifying this function, we get it also equal to 1/2 of tangent of squared of x minus ln of absolute value of secant x plus an arbitrary constant. So that was our final answer. So next, how about we're going to integrate a function of cotangent raised to the power of 3 of x dx. So as you can see here, our in here is 3, which is an integer. So what we're going to use, the formula is that cotangent squared of x is equal to cosecant squared of x minus 1. So therefore, by substituting as what we do in the previous example, we're going to break down this function to use this formula. So therefore, it would be equal to the integral of cotangent squared of x times cotangent of x dx. So therefore, we're gonna substitute the value of our cotangent squared of x, which is equal to this. So therefore, where it would be equal to cosecant squared of x minus 1 times cotangent of x dx. So by distributing the cotangent of x each term, so we have the integral of cosecant squared of x times cotangent of x dx minus the integral of cotangent of x times 1 simply equal to cotangent of x dx. So as you can see here, as you notice, the derivatives of cotangent of x is simply equal to negative cosecant squared of x, which is equal to this function. So therefore, we're gonna use our cotangent of x as our u. So we use the way of du and u representation and substitutions. So we're gonna represent our u as equal to cotangent of x. So therefore, by finding the derivatives of cotangent of x, simply equal to negative cosecant squared of x dx. So therefore, our dx value here is equal to du over negative cosecant squared of x. So by substituting this to represent values to our original values, so in the first term we have here the integral of cosecant squared of x. Our cotangent x here is, we're gonna represent this as our u. Then our dx, we have the value that is equal to du over minus cosecant squared of x. So we're gonna cancel out the cosecant squared x here. So what's remaining is the negative, because we have negative here, negative integral of u du. Then in our next term, our cotangent of x dx. So what we're gonna do here is substitute the sine and cosine value of cotangent of x. So the ratio of identities of cotangent of x is equal to cosine of x over sine of x dx. So as you notice here, the derivatives of a denominator, which is cosine of x, is equal to the numerator. So therefore, we're gonna represent also here our u as equal to sine of x. Then by finding the derivatives, our du here is equal to cosine of x dx. So therefore, this cosine of x dx is equal to du. So what is remaining here is equal to the integral of this is equal to du, which is our sine x here is we're gonna represent as our u. This become u. So therefore, by integrating in this term, we're gonna use the power formula of integration. So therefore, it would be equal to u raised to the power of 2, which is we're gonna add the power by 1 and divide the function by its exponent, which is 2. Then here in this term, we're gonna use the logarithm formula of integration. So therefore, it would be equal to the ln of absolute value of u plus an arbitrary constant. So therefore, by substituting the original value of u, we have the first term, our u value is equal to cotangent of x. It's become negative 1/2 of cotangent, which is raised to the power of 2, or cotangent squared of x, then minus the ln. Our next term here, our value of u is equal to sine x. So therefore, it's gonna be absolute value of sine x plus an arbitrary constant. So that was our final answer. So next, how about we're going to integrate a function of tangent raised to 4 of x dx. So our n here is equal to 4, which is an integer. So what we're gonna use also the formula of tangent squared of x is equal to secant squared of x minus 1. So therefore, to make this formula satisfied to the original formula, we're gonna break down this original function. So it would be equal to tangent squared of x times tangent squared of x. So therefore, by substituting this function to this function, so we have to be equal to secant squared of x minus 1 times tangent squared of x dx. So by distributing the tangent squared of x, so we have in the first term, we have going to integrate the secant squared of x times tangent squared of x dx, then minus by multiplying tangent squared x to 1, so it would be going to integrate the tangent squared of x dx. So as you can see here, in this term, if we're going to get the derivatives of tangent of x, so it would be equal to secant squared of x. So therefore, we're gonna represent this as a u, and we use the u and du representation and substitution. So in the first term, we have our u is equal to tangent of x. Therefore, by getting the derivatives, we have the du of tangent x is equal to secant squared of x dx. So therefore, our secant squared dx is equal to du, and our tangent of x is equal to u. So therefore, by substituting, we have this both is secant squared x dx is equal to du, and our tangent of x is equal to u. So therefore, we have here squared here, so it's become raised to the power of 2. Then in the next term, we have here tangent squared of x, the integral of tangent squared of x dx. So what also we're gonna do here is to substitute this formula. So by substituting, we have the integral of secant squared of x minus 1 dx. So here, by simplifying these integrals, so we have u raised to 3 over 3 minus, by distributing the integral sign, we have the integral of secant squared of x dx minus, we have minus outside here, then minus the integral of dx. So therefore, by simplifying, we have our value of u here is equal to tangent. So we have 1 over 3 tangent of x raised to the power of 3, or tangent cube of x, minus then the integral of our secant squared of x, as in our formula, is simply equal to tangent of x. Then the integral of dx is simply as x. So therefore, then add an arbitrary constant. So therefore, in simplifying, so we have 1/3 tangent cube of x. Then by distributing the negative sign, so we have minus tangent of x plus an x plus an arbitrary constant. So that was our final answer. So next argument here in transformation of trigonometric formulas. If we're going to integrate a function, for example, tangent of m of x times secant raised to the power of n of x dx, or a function which is cotangent raised to the power of n of x, then times cosecant raised to the power of n of x dx, where our in here is a positive even integer. So what formula we're gonna use here is the same as the formula we use in the previous examples. So for example, if we're going to integrate a function of tangent squared of x times secant squared of x dx. So this is our m and this is our n, where our n here is an positive even integer. So what we're gonna do here is use the formula of tangent squared of x is equal to secant squared of x minus 1. So this is 4. So what we're gonna do here is we're gonna break down the function of secant, the secant function. So it would be equal to tangent squared of x times our secant squared of x times secant squared of x dx. And by this formula, we're gonna substitute the value of secant squared of x. So we have the integral of tangent squared of x times our secant squared of x here is equal to tangent squared of x plus 1, then secant squared of x dx. So as you can see here, it's easy now to integrate. So first, what we're gonna do is to distribute the each terms. the tangent squared x and secant squared x. So we have, therefore, tangent squared x times tangent squared x is equal to tangent raised to 4 of x, and then times secant squared of x dx. And then in the next term we have addition here, so we have tangent squared x times secant squared x. So we have the integral of tangent squared of x times secant squared of x dx. So as you can see here, same aspects as our previous examples, we're gonna use here our u as equal to our tangent x, because the derivatives of the tangent x is equal to this secant squared x. So both terms we're gonna use our u is equal to tangent of x. So finding the derivatives, we have du is equal to secant squared of x dx. So this function is equal to our du, and this function is equal to our du, also equal to our du. So in substituting our represent function to the original function, so we have here our tangent of x here is equal to u, which is raised to the power of 4, because this function also we're gonna write this as tangent of x raised to the power of 4. So therefore this function is equal to this du, and then plus also our tangent x is equal to u, which is raised to the power of 2, then this is equal to du. So now as you can see, it's easy to integrate using the power formula of integration. So in the first term, the integral of u raised to 4 du will be equal to u raised to 5 over 5, which is adding the exponent by 1 and dividing the function by its exponent. Then also the same in the next term, we have u raised to 3 over 3, then plus an arbitrary constant. So in simplifying, we have 1/5. Our u here is equal to tangent x, tangent of x raised to 5, or tangent 5 of x, plus 1/3. Our u is equal to tangent x raised to 3, or tangent cube of x, plus an arbitrary constant. So that was our final answer. So next, how about if we're going to integrate cotangent of squared of x times cosecant of 4 of x dx. So you can see this is our aim in our formula, and this is our n. And as you can see, our n is equal to even positive integer, which is 4. So what we use here is also the formula of cotangent squared of x is equal to cosecant squared of x minus 1. And then to make this formula satisfied to the original formula, what we're gonna do here is to break the function of cosecant, which has a power of n. So it would be equal to cotangent squared of x times cosecant squared of x times cosecant squared of x dx. So therefore, by substituting from this formula, we're gonna simplify our cosecant squared of x is equal to cotangent squared of x plus 1. So therefore, by substituting this our formula to this our original functions, so it would be equal to cotangent squared of x times cotangent squared of x plus 1 times cosecant squared of x dx. So by simplifying, we have cotangent squared of x times cotangent squared of x times cosecant squared of x. So it would be equal to the integral of cotangent raised to 4 of x times cosecant squared of x. Then in the next term we have cosecant squared of x times 1 times cotangent squared of x. So we have cotangent squared of x times cosecant squared of x dx. So by distributing the integral sign, so we're going to integrate cotangent raised to 4 of x cosecant over dx, the integral of cotangent squared of x times cosecant squared of x dx. So as you can see here in this function, if we're going to get the derivatives of cotangent of x is equal to cosecant squared of x, so we use here is the way of u and du representation. So we're gonna use our u in both terms is equal to cotangent of x. So by finding the derivatives of our u, so we have du is equal to cosecant squared of x dx. So by substituting this our represent functions to the original function, so we have the integral of cotangent 4 raised to 4 of x. So where our cotangent of x is equal to u, so it's become raised to 4. Then this function cosecant squared of x dx is equal to our du. Then the next term we have the integral, also our cotangent of x is equal to our u, which is raised to 2. Then times our cosecant squared x dx is also equal to du. Then in this function, both terms we can easily use the power formula of integration to integrate this function. So we have the integral of u raised to 4 du is simply is equal to u raised to 5 over 5. Then plus the integral of u squared du by simply adding the exponent by 1 and dividing the function by its exponent. So we have u raised to 3 over 3, then plus arbitrary constant. So therefore in simplifying we have 1/5. Our u is equal to cotangent of x is x, so which is raised to 5, so therefore it's raised to 5. Then plus also 1/3 of our u, which is our u is equal to cotangent of x, which is raised to 3 here, so it is raised to 3, then add an arbitrary constant. So that was our final answer, and that is for this video. Don't forget to like and subscribe for more video.